Okay, so I'm going to do one more example of a Kirchhoff's rule problem. This is just one of the chapter problems from the book, problem number 34. We've got a current a circuit with 2 loops, a 9-volt battery and a 12-volt battery, and 3 resistors, 25, 48, and 35 ohms, and we want to know what is the current through each one of the resistors, R1, R2, and R3, so the current through each branch of the circuit. If we look at this circuit and figure out what the batteries are trying to do, this 9-volt battery is trying to push current this way, and this 12-volt battery is trying to push current this way. So it makes sense to call the current this way around this part of the loop I1, and the current this way around this part of the loop I2. And so I1 comes around the loop until it gets to this junction, I2 comes around the loop until it gets to this junction, and in the middle they sort of combine together to push current this way through the loop. So we'll call that current in the middle part where the 2 loops overlap, I3. So the junction rule tells us at this point in the current where this point in the circuit where the currents as we've defined them come together, I1 plus I2 equals I3. And now we need to just pick our points where we're going to start, pick our directions that we go around our loop, and follow our currents until we get back to where we started. So I'm just going to pick this point for both of my loops. I'm going to do one loop that goes clockwise around this top part of the loop along with I1 and then I3, and then another one that goes starting here counterclockwise around this bottom loop with I2 and then I3 across the middle. So let's start here in our top loop. What have we got? What do we encounter first? The first thing we encounter is a 9-volt battery, and we're going from negative to positive up the potential difference. Our potential is increasing, so that's a positive 9-volt increase in electrical potential. Then we go across the resistor. That's a potential drop of minus IR, so minus I1 times 25 ohms. Then we go through the junction, and we're in the part of the circuit where our current is I3. We go across another resistor, so there's a potential drop of minus I3 times 48 ohms. And then we get back to where we started, and we go around a full loop. Kirchhoff's loop rule says that the total potential drop is 0. So if we do the thing where we throw away our units just to clean up our equation here, and put everything in an algebraically simplified form, I'll rewrite this as 25 ohms times I1 plus 48 ohms times I3 equals 9 volts. Put the 9 on the other side, divide through by the -1. Everything's got a plus sign. So there's our second equation. We've got one equation from the junction rule, one equation from loop 1, and then we'll do the same thing for loop 2. We'll start at that same point here. We'll go around our loop this way, coming back to where we started again. So the first thing we encounter is a 12-volt battery. We're going up from negative to positive, so there's a plus 12-volt potential difference from here to here. Then we go around and we go through a resistor, so there's a potential drop of I2 times 35 ohms. Then we go through our junction, through the part of the circuit where the current is I3, and we go across a 48 ohm resistor, so there's a potential drop of I3 times 48 ohms, and then we're back to where we started here, so the total potential difference is 0. So if, again, we rewrite this, throw away our units for now, just to keep things tidy, I've got, what have I got? I've got 35 ohms times I2 plus 48 ohms times I3 equals 12 volts. And again, everything's got a positive sign. We divide through by -1. So there's our 3 equations in 3 unknowns, I1, I2, and I3. I'm just going to make the transformation from I1, I2, and I3 to X, Y, and Z. And I'm going to let Wolfram Alpha solve this. If we wanted to solve this ourselves, what I would probably do is solve this for I1, plug it in here, and then you've got an equation in I2 and I3. It looks like the easiest thing to eliminate would be I3, so I'd probably combine these two, eliminate I3, and solve for I2. But I'm not going to do that. I'm going to let Wolfram Alpha do the hard work for me. So let's see if I can switch over to... yeah, so we're in Wolfram Alpha. What are our equations? Our equations are I1 plus I2 is I3, so x plus y equals z. Our other equation is 25I1 plus 48I3 equals 9, so that's 25x plus 48z equals 9. And our third equation, 35I2, so 35y plus 48z equals 12. Wolfram Alpha will solve that system of simultaneous equations for us exactly and give us a bunch of fractions. We could poke them into our calculators ourselves or just ask Wolfram Alpha for the approximate form. And what we get is x equals 0.045. So let me go back to my camera. X, which is I1, equals 0.0455, so we'll say 0.046. Y, which is I2, is about 0.118, so we'll say 0.12. And I3 is about 0.16. All of these now we'll put our units back in amps because they're all currents. And going back to our diagram, what does that mean in terms of the directions? I1 was this way, so 0.046 amps is the current through resistor 1 towards the right. I2 was this way, so the current through this resistor down here is 0.12 amps that way, and in the middle, I3 0.16 amps that way. All of our currents came out positive, which means we guessed right at the beginning for what the directions are of all of the currents in the circuit. Our intuition about which direction current would flow is correct. I took the liberty of, I'm sorry for that noise I just made, of writing down the solution from the book. 0.46 amps that way, 0.16 amps that way, 0.12 amps that way, so that answer is right. And we got the answer not only with the right numbers, but with the right directions. So that is that's Kirchhoff's rules. Like I said, not pleasant, not a whole lot of fun, but a sort of necessary evil. And so I'll assign a couple of those for practice. Like I said, I probably would never give you one of these on the exam, both because it's super easy to make a sign mistake, and secondly, it's super easy to screw up some little tiny bit of algebra when you're solving a system of simultaneous equations. So it's not really, to me, worth the effort of making you struggle through this with an exam, but we will do one or two for homework because it's an important thing to do at least once in your life. It builds character. So I think that's the last example I will do of that. I'll assign a couple of homework problems, and then we'll move on to some more interesting aspects of circuits later on next week.